here with our second talk of the day. And it is my pleasure to introduce Dr. Andrew Lampinen, who travels to be with us in person from London. And he is a senior research scientist at Google DeepMind. And he holds a bachelor's degree in physics and mathematics from UC Berkeley, and he did his PhD in cognitive psychology at Stanford University. And his research interests include generalization, cognitive flexibility, and efficient learning, and also he's interested in how language, among other things, facilitates disabilities. The stage is yours.
Awesome. Thank you for that great introduction, and glad to be here with you all. So yeah, today I'm going to tell you a bit about some of the work we've been doing on comparing language models to humans in topics like reasoning and grammar. It may echo some of the themes that you heard in the workshop earlier, because we do a lot of related work. And my goal for this talk is to give you a pretty high-level flyby of some of the themes that we're interested in. So I won't have time to go into too much detail about these things, but I want to give you a bit of a big picture view of how I think about language models and what they do, some topics in grammar and capabilities and reasoning and how we can think about these skills. So first of all, what are language models? Well, as you saw in the workshop earlier, language models are these tools that are trained to predict what language comes next, and everybody's been getting excited about them recently. And in particular, what a large language model is it's a neural network that's trained on a bunch of text taken off the internet, usually written by humans. And the model is trained to predict that text as follows. So you give the model a sequence of words as input, like training large models is not, and then the model is going to try to make a prediction about what's going to come next in that text. So the way that works is that the model will propagate forward through the layers of the network, and at each step, it's going to integrate some information from earlier in the text in order to improve its prediction of what's coming next. And finally, at the output, it'll produce a probability distribution over some words that could come next. And then you'll give it an answer about which word actually comes next. Perhaps training large models is not easy. And then the model can learn from this process in order to make better predictions in the future. So the idea of predicting what comes next in some text is not a particularly new idea. People have been doing it for 30 years or so. But what makes the current language models different is a particular feature of how they integrate information from earlier in the text to the rest to make better predictions now. And so I wanted to dive into that feature in a little bit more detail. And this is the operation in transformer models that we refer to as attention, although as you'll see, it maybe doesn't have so much to do with how we think about attention in humans. The way this operation works is that we have a current token or a current word that the model is trying to predict what will come after that word. And then there's going to be some earlier words in context. And the attention operation is a way that the model can sort of ask for information from the earlier words to help improve its prediction of what's coming next. So the way this works is that the model produces a query vector, so a set of numbers that you can think of as encoding a kind of question about what was earlier in the sentence. For example, it might ask, what's the subject of this sentence? And then each of the earlier tokens in the sentence will produce two vectors, a key and a value. And the way the attention operation works is that the keys can kind of tell about whether those values will answer the query or not. And the attention operation first compares the query to each of the keys. And perhaps the query doesn't match the key on the right very well, but it does match the key on the left pretty well. And then the values corresponding to those keys will get weighted according to how well the query matched the key. You can think of that as being like, well, if this is the answer to the question, we should bring it forward, and if it's not, we shouldn't. And finally, those weighted values will get added up, and together the result will be passed back to help the model make better predictions. And so this turns out to be a very effective way of allowing the model to flexibly get information from earlier parts of the text in order to make better predictions about what comes next. And this is the operation that has made modern language models so much more powerful than the ones we had before. So, sorry about that. So language models use many layers of this kind of vector attention operation to earlier text in order to predict what comes next. And a natural question that might come to your mind when you see something like this is, well, what could any of this weird vector arithmetic, attention, predicting what comes next stuff have to do with human cognition? I'm not going to fully answer that question, but I do want to hint at two possible reasons you might think this is interesting. The first is that predictive processing is actually something that we think across a broad range of tasks and domains and modalities is kind of a fundamental principle of what the brain does. So from vision to reinforcement learning to language, and maybe even under some accounts a sort of unifying theory of what the brain does, we think that the brain is making predictions about what will happen next, using that as a learning signal, using that as a way to efficiently encode information, and so on. And the other reason that prediction might be a useful learning ability is perhaps a more empirical observation, or a more not obvious, something that's not obvious at first principles, but is kind of obvious in retrospect, which is that prediction is powerful because in order to make accurate predictions about everything, you have to understand a lot of things. And in particular, the amount of information you have to understand to make accurate predictions about text is quite surprising. So to give you some examples of this, you have to understand world knowledge in order to accurately predict the continuation of sentences like the capital of France is. You have to understand processes, how people do things in the world, to predict information about how people would describe a process. You have to understand the relationships between languages in order to accurately predict how someone would translate something. You have to understand how to reason in order to predict, for example, what the end of a mystery novel is going to be. And you have to understand mathematics in order to predict, how someone would prove some difficult theorem. So if a model could accurately make predictions about what would come next in text consistently, it would have to understand all of these things. But of course, the key issue there is how accurately you're making those predictions. And you can make okay predictions about what will come next without understanding any of these things. And part of the issues about language models are going to be how accurate are the predictions they're making across these kinds of cases that involve these capabilities. So because prediction yields these abilities and because people have fun playing around with language models, hopefully you did earlier too, there's been a lot of discussion in the recent years over what these language models can actually do. What are their capabilities? Can they do things like reasoning? Do they understand language or grammar? And this debate has been going on both on Twitter, obviously, but also in the academic literature. And the point I'd like to make in this talk is that these comparisons are generally predicated implicitly or explicitly on what humans can do, how we think about human reasoning, how we think about human knowledge of language and grammar. And often the claim is that, well, language models are not human-like, they're missing something about reasoning or grammar that we have. So what I'd like to try to do in the remainder of this talk is to raise two questions about this. The first is, how would you make a fair comparison between a language model and a human? How would you ensure that you were matching them up in an appropriate way to compare their capabilities? The second is, what could it be that you would learn from this? And I'm going to do this by talking about two case studies of work we've done, looking at the grammar and reasoning capabilities of these models, and try to come back at the end to reflect on why we should care about any of this. So first, what are the challenges and opportunities of comparing humans and language models? What I want to do in this section is to take some inspiration from comparative psychology. So many of you may know this already, but comparative psychology is the discipline that studies the comparative abilities of different animal species with each other, or animals and humans, and tries to understand something more fundamental about the principles of intelligence or the differences in intelligence between different systems by doing that. And one of the key aspects of comparative psychology is that it's really important when you're matching up two systems to ensure that you're testing them in a way that is fair to both of them. So to give you a concrete example of this, imagine that I saw a squirrel in my backyard. And I put a Rubik's Cube in front of it. Maybe the squirrel is confused, it doesn't solve it. And so I tell you, aha, I've proved that squirrels don't understand relations. Well, you as a skeptical cognitive scientist might ask me some questions like, was the squirrel motivated to solve the problem, or was it just trying to go eat some nuts in the tree? Was the task understandable to the squirrel? Did it get what I was asking it to do? Could its cute little paws even manipulate the Rubik's Cube? Are the affordances of the problem, do they afford the problem in a way that the squirrel can manipulate it? And so on. That is, how do we ensure that this is a fair test of what the squirrel is able to do at its best, rather than just sort of a trick that it can't understand or doesn't want to do at all. And what I'd like to suggest is that when it comes to language models, like this stand-in for our chinchilla language model at DeepMind, we have to ask the same kinds of questions. So if someone puts a task in front of a language model, and then the language model fails, and the person says, language models don't understand relations, let's say, you might need to ask the same kinds of questions, like, was the model motivated, in scare quotes, to answer the problem correctly? That is, the models are trained on many aspects of the text distribution on the internet, as Marcel alluded to earlier, and that means that they're trained to both do things like produce good reasoning, but also produce all the bad reasoning and sarcasm and jokes and everything else that humans produce on the internet. So how do we get the model into a context where it's trying to produce the best answers in some sense? And how do we ensure that the task is clear to the model? For example, maybe you need to give some example shots for the model to know what the answer pattern is supposed to be. And how do you make the model work how do you make the task work for the model, and so on? That is, just like for the animals, how can we give the language model the best chance to show off its capabilities? So, first question for the talk is, what evaluation methods will allow fair comparisons between humans and models? But this raises a more fundamental question, which I think is an interesting and still unsolved topic in cognitive science, which is, what does it mean for a system to have a capability or a competence? We use this term in many different ways. For example, we might say a system is capable if basically it's robust. It can succeed even in the worst case. And people often think about vision capabilities, for example, in this way. If there's a case where the system makes a mistake, even if those cases are very rare, like adversarial examples in computer vision, we would say perhaps the system is missing something about what it means to have a capability for vision. But on the other hand, there's cases where, when talking about humans, we would ascribe a capability to someone, even if they can only exhibit that capability very, very rarely. For example, we might say that a scientist has the capability for being a great researcher, even if they only come up with one brilliant idea or a handful, or even if they never do in some cases, but we think that they could. Or you could think about defining capabilities as behavior and expectation over some distribution, but then you have to think carefully about what that distribution is and whether there are systematic errors in certain cases and so on. So a really important question is, if you're investigating some sort of capability or competence, how would you even define that capability? Again, I don't think that this question has been answered, but in cognitive science historically, comparisons between different systems have offered an opportunity to at least refine our understanding of a capability. For example, our understanding of language has been shaped a lot by experiments comparing how humans and chimpanzees and other closely related species understand recursive structures that we think are important in language and understand and are able to learn and generate new sentences. And comparisons between human intelligence and behaviors and computational models have shaped how we think about human capabilities and how humans arrive at the answers that we do. For example, there's this field of bounded rationality, which basically says humans are trying to do something perfect, but they're limited by their computational resources and so on. And so they're forced to do something that's sort of a trade-off between the resources that they have and what they're trying to achieve. And by comparing to these models, we can maybe understand better what it is that the computational problem the brain is trying to solve. And so the second question I want to ask in this talk is, what could we learn from comparing humans and language models? All right, that's enough introduction spiel. So let's dive into some empirical studies. But before we do that, I want to pause really quick and see if there are any questions. Yes. Yeah, that's a great question. So I think we need a better terminology for talking about language models, because I often want to use terms like motivation and understanding that are not really appropriate. I guess I would define these terms kind of behaviorally, as in, I ascribe understanding to, let's say, a student that I'm teaching in a math class if they can answer questions, and then when I probe them on those answers, for example, I say, oh, can you explain why you did this step? They say they can give a good explanation for that. And in some cases, I think we can evaluate language models in the same way, but there's also, I tend to think of most human capabilities and language model capabilities, this will come out later in the talk, as fairly graded things. So I don't think something like understanding is dichotomous, right? Like a student might understand a math problem in the sense that they could answer it correctly, perhaps, but maybe a mathematician would have a deeper understanding of it because they would also understand how it relates to other things. Or maybe the student would think they understand it, but there's certain aspects of it they don't get correct even if they get the right answer. So I think that understanding is sort of a fuzzy term, but here I just mean that, you know, for example, it's something you could assess by like seeing, if you ask the model, what is the task you're trying to do? Does it produce an answer that's accurate? That might be evidence that the model is understanding what you are asking for. Cool. Any other questions? Yes?
How do you make sure that the setting for the model versus for humans is similarly certain or uncertain?
Yeah, that's a...
In terms of context, individual differences, situation, time as well.
Yeah. I'm basically going to say that I don't know. So yeah, I think you'll see in this section an example of one instance where I think that there was a comparison that was misleading, and maybe there were aspects of it that could be compared. But it's very hard because the systems are so different to ensure that you're doing perfectly fair comparisons. And in comparative psychology, when we think about, you know, how do you compare behavior between, let's say, rats and humans, for example, how do you compare how they solve some sort of reinforcement learning task? There's still a lot of ongoing work on it that's debating, like, well, what exactly is going on in this particular case? So I think probably with comparing language models to humans, similarly, it's going to take some empirical work to see, well, maybe if they do the task in this way, it kind of matches humans better, and maybe that means that if you're trying to get more human-like behavior, you should set things up in this way or something. I don't think we have the full answers to that at all, and in a lot of cases, it may just be impossible to make a perfectly fair comparison. So, you know, with comparing rodents and humans, for example, you just, like, you explain the task to the humans, you don't explain it to the rats. You can never make that a perfectly fair comparison. It's just a feature that you have to accept when you're doing that kind of work. But great question. Okay, cool. So maybe I'll press on. So the first topic I'm going to tell you about today is some work we did on recursive grammar structures. So recursive grammar structures, and in particular center embedding, are a particularly interesting kind of linguistic structure where you take a phrase and you embed some other phrases in the middle of it. So for example, we could have a phrase like the keys are heavy, let's say, and then we can split that phrase up, take the noun phrase part, the keys, to one side, and we can put some other stuff before the verb, like the keys that the man by the cabinet holds are heavy. And what's interesting about these sentences is that they're one of the rare cases, in English grammar at least, where there's a strong separation between how close together two things are in the sentence, that is the linear distance between them, and how closely related they are syntactically. So in particular, no matter how much stuff you put in between this noun keys here and this verb are on the right, those two things still have to disagree. So however far apart they are in a sentence, there's a syntactic dependency between them that has to be respected. And according to classical theories of linguistic competency, at least, this is a critical test of recursion, because one way that you could solve this is by sort of maintaining a stack of the phrases that you've observed in this sentence that's sort of structured like this parse tree you can see on the left. And then when you get to the end of one of the phrases in the middle, you pop all the way back up that stack recursively to get to the top of the tree and see what the link you're going to follow next is. So because of this, this has been considered a key case for debating, first of all, linguistic abilities in humans in general, the properties of certain model systems, in particular Chomsky's grammar, and whether neural networks could capture those abilities. And there's been some more recent work on this topic. Was there a question somewhere? Yes. Great point. So that's actually going to be what I talk about on the next slide, more or less. Yeah, so the kind of agreement that we're looking at in this case is this sort of agreement between singular nouns and their verbs and plural nouns and their verbs. And the paper, sorry, I flashed this paper really quickly. There was this paper showing that language models perform below chance on these constructions and humans don't. And in this paper, they showed that some kinds of center embedding are harder than others. And they considered sentences like this one here, where there's an outer dependency, so there's a noun and then a verb at the end. There's an inner dependency, so a noun here and a verb here, and then there's another distractor phase embedded in the middle of the inner dependency. And what they showed is that, right, so as you were alluding to, it depends on which of these nouns are singular or plural, how the verbs should match up. And it turns out that the difficulty of these tasks, right, so this sentence, for example, the outer verb is plural, the inner verb is, the outer noun is plural, the inner noun is singular, and then the distractor noun is plural. And it turns out that the difficulty of these sentences for humans depends quite a lot on what the pattern of these singular and plural verbs is. And the hardest cases are when you get mismatches where the inner dependency is singular, but the outer dependency and or the distractor disagree. So yeah, it depends a lot on what the exact pattern of dependencies is, how hard these tasks are. So in this original paper, what they did was they compared humans and language models on these dependencies. This is showing you the human error rates. So lower is better, means they're more accurate. And what you can see is that the humans are generally better than chance in these cases, although maybe there's some cases where they're close to chance. And the language model is better than chance in many cases, but there's one particular case where it's doing worse than chance. And so the authors considered these two cases and said, aha, transformers perform below chance in these tasks, unlike humans. This is a bit of an interesting conclusion from these data, but the point I'd like to make is that there's a question about whether the evaluation is fair in this case. So the researchers who did this work are fairly experienced in the field of cognitive psychology, and so they probably took out their experimental psychology textbook and they wrote a fairly long methods section on the methods they use for performing this task. And just to pull out some details from that, after each trial, participants got feedback. They were given 40 training trials before the experiment started, where they saw all structures and so on. And by contrast, when they evaluated the language model, well, you know, there's not really a textbook on experimental AI yet, so maybe because of that, they didn't think that carefully about the experiments they were doing. And they evaluated the model with no prompt, that is 0 shot, with no training trials and no context. And I think that this is a kind of unfair comparison because the human comparison for 0 shot eval without any context would be something more like shouting the question at a stranger you see on the street and then seeing whether they give you the right answer. And you can find some pretty funny videos on YouTube of people failing to answer fairly simple questions in this kind of context, although I assume those examples are cherry-picked. So what we wanted to do in this work is to see whether language models could do better given a few examples like the humans were. So again, I'm showing you on the left here, the human error rates, lower is better. And this is given 40 training trials. And this is with a different language model than the original paper used with our chinchilla model, the error rates that the model gets with no prompt. And what you can see is, like in the original paper, there are some cases where the model is doing okay, but there are certain hard cases where the model is doing much worse than chance. However, if we give the model just 2 examples in the prompt, the model already does better than chance in every case. And if we give it 8 examples, it does quite well across all the cases, very low error rates. So if we few-shot prompt with 8 examples, that is 20% of the ones that the humans saw, and we don't give any prompt examples in the hardest grammar structures, unlike the humans, then the model actually performs comparably in the hardest condition to how humans perform in the easiest condition. So, okay, maybe these tasks aren't hard enough for the model. We can make them the sentence deeper by just adding another layer of embedding at top. And even if we do that, it turns out that the model still makes fewer errors in most conditions, maybe all conditions, than the humans do in the easier, shallower tasks. So what this suggests is that actually, at least on these kinds of stimuli, language models might match or exceed the human capability for recursive grammar processing. But the answer that you'll get depends fundamentally on how you compare them. And if you are setting up an experiment where your humans get some feedback, get some training, get some instructions, it's worth thinking carefully about how to ensure that the language model is getting that fair context. One thing I want to highlight here is that I don't think the authors were trying to do something malicious. I think it's actually quite easy to slip into these unfair comparisons, especially if you've been working with cognitive models for a long time. So I want to make a distinction here between cognitive models and foundation models. So cognitive scientists are used to working with these cognitive models, like this quite old model of recursive grammar processing from the early days of neural networks, that are trained and tested to do some particular task, like trained only to do subject-verb agreement in sentences. And for these kinds of models, you don't need to give context. You can evaluate zero shot because the model sort of knows, is motivated, in scare quotes again, to do the task from the training distribution. That's all it's ever learned to do. But language models are these sort of foundation models that are trained across a broad range of contexts. So they're also trained to do things like predict memes that have bad grammar and so on. And what that means is that you need a way of getting them into a context where they're making the best predictions they can, such as few-shot prompting. So I think that part of what comes up here and why these kind of issues come up in a variety of work is that it's easy to see a language model and think about it in the way that you've thought about cognitive models previously and just test it like you would any other cognitive model. And that's exactly what happened in this work. These authors had done some previous work with a cognitive model that was trained to do this task, and they just switched it. They just said, oh, we'll just test a language model on it just like we tested our cognitive model, and that'll be a perfect comparison. But I think you actually need to think about it a little bit differently. So to summarize the results from this section, we need to be careful when we compare language models and humans to make sure that that comparison is fair, just like in comparative psychology. And it seems in this case like a human-level competency for recursive grammar doesn't require some sort of innate merge or recursion ability, which is sort of a linguistically relevant claim. And indeed, if you looked at these two plots, the left one is humans, the right one is models, and asked you which one has a real capability for grammar, you might even say it's the one on the right, much lower error rates. But of course, it's worth noting in this context that this is kind of an unfair comparison to the humans because these language models learn from way more language than any human ever experiences in their lifetime. So these kinds of comparisons can't fully resolve questions in linguistics about what needs to be learned, what needs to be innate, what could be learned. So it's an open question to what extent you could get a neural model to learn these kind of processing strategies from a more reasonable amount of data, and whether richer embodied experiences beyond language might help. That's a research interest of mine, but not something I'm going to talk about today. Cool. So next, I'm going to progress to talk about some work we've done on content effects on reasoning. But before that, are there any questions? Yes.
I'm just really curious about how come the human I don't know if understanding the differences, because surely, like from a sort of experiential perspective, you must have recruited sort of native speakers, and yeah, I just want to know, like, they kind of mentioned about
Yeah. So that's a fantastic question. And I think there's a few reasons for this, but the main one is just that these sentences are actually really weird. So center embedding is actually a very rare occurrence in spoken language. It basically never occurs in spoken language to this depth. It only occurs with depth 1. And even in written language, it's quite rare, just because it's quite confusing to process. So if you read through the sentence, the actors that the mother near the students watches meet the author, it's a very parsing which verbs go with which nouns is kind of confusing. And because of that, people don't tend to talk this way, and we also aren't used to parsing these sentences. But I think that some of the difficulty also depends on the particular way that the humans were evaluated on this task, because the this was actually an experiment that was done in an fMRI scanner, if I remember correctly. And so the participants were fixating on the screen and seeing one word at a time. So in some sense, this is a good way of testing whether they're maintaining that state recursively, because you are ensuring that they can't look back at earlier parts of the sentence and see, and like think about what the pairings are in order to get an accurate answer. But that also means it's a really hard task on their working memory for them to maintain everything that's happened in the sentence. You're much more likely to get noise and interference and so on. And there's been some modeling work, not by me, but by some people in Roger Levy's lab at MIT, that show that actually if you want to model human performance on these kind of tasks better, like match the human error rates better, you can do it by taking a language model and injecting some noise into it as though like some of the words got dropped during the encoding process, and that kind of matches the human errors better. So I think it's maybe partly that these sentences are just weird and hard, and partly that there's a high working memory demand and people just aren't fully up to that. Great question. Yes.
Are there any differences between languages?
Are there any different? So, okay, this is a fantastic question, and I'm not going to get into the details of it because I am not a linguistics expert, but there are big differences between languages. And an important caveat to this is that the humans were evaluated in Italian, which is actually a language that has grammar structures that are more similar to this more frequently. And the language models were evaluated in English. So I followed the original authors in doing that, but we do note in the paper that that's kind of a caveat because there actually might be things about the languages themselves that make this a kind of unfair comparison in other ways. Great questions. But yes, different languages, very different properties with respect to this sort of like distance of dependencies in the sentences and stuff. Yes?
How can you handle what is really learnable from data with respect to these grammatical structures from what we add on top of this, like what the model actually learns with, for instance, different decoding schemes, more engineering tricks?
Yeah. Yeah, that's a great question. So there's a few things that you have to be careful of here. So one is you have to think about like what's learned in the prompts. Like if you give examples, like are those giving away the answer on certain kinds of examples? Does the model do better on the kinds of structures that appear in the prompt, for example? We look at that in some of the analyses in this paper. The decoding schemes, we kept the decoding scheme constant across all the experiments here. So that doesn't change things, but there are cases where that can make a big difference in how you change and how you get in the answers you get. One property that makes this a little bit simpler is that here it's a multiple choice, like should this verb be singular or plural? And so you can just score those answers and see which one the model thinks is better. Where the decoding scheme matters a lot is when you're doing actual text generation. And in those cases, it's like quite sensitive, especially with chain of prompt and other chain of thought and other prompting strategies like that. It's quite sensitive to exactly the decoding scheme you use. Great question. I think in the interest of time, I might press on, and then we can come back at the end for some more general discussion. Cool. So next, I want to tell you about some work that I'm a little more excited about because I care more about reasoning than grammar. And this work is about content effects on reasoning. So what is reasoning? If you look it up on Wikipedia, like any good scholar would, you might find that it's some sort of capacity that has to do with logic. Maybe it has something that humans are uniquely good at, and maybe you decide, it's like something like a uniquely human capability for using logic. But in cognitive science, there's actually been a long debate over many years about the extent to which humans are logical reasoners, and this is often called the rationality wars. So on the one hand, there's lots of cases where you can show that humans do sort of rational or semi-rational things, and people use this to say, humans are inherently rational. That's one of our properties. But on the other hand, there's lots of well-known cases where human behavior systematically breaks down, is irrational in well-known ways, has certain biases that we know are very common. And so on the other side of the debate, there are people saying, well, humans are just naturally irrational. That's a property of our cognition. And one key feature in the debate is the issue of the role abstract logic plays in our reasoning versus the effects of content on our reasoning. So logic itself is independent of content. If you have a logical proposition like if X then Y, the implications of that don't depend on what the variables x and y represent. And a system that reasons purely using logic, that is abstractly, has the nice property that it's going to be systematic. It will arrive at the same conclusion regardless of what the content is if you start from the same premises, the same logical structure. And that's a nice property for a system to have because you can kind of guarantee what it's going to do. And so the question is, well, are humans systematic in this way? Are we purely abstract reasoners? That is what's going on in our heads some sort of, logical inference over propositions, or is it perhaps something a bit messier? I'm going to show you two examples of ways in which people are affected by the content of what they're reasoning about and not just the logic. So the first is, if you give people syllogisms, a very simple kind of logical structure, they tend to judge whether that syllogism is logically valid or not by the content of the argument and not just its logical structure. So in particular, if you consider a syllogism like the following, all students read, some people who read also write essays, therefore some students write essays. Quick, is that valid or invalid? Okay, most of you did well. And then if you give a syllogism like all students read, some people who read are professors, therefore some students are professors. Well, maybe if you look at these two syllogisms have the same logical structure, but maybe it's easier to see in the second that it's invalid because the conclusion is kind of suspicious, right? Some students are professors. Maybe that's true, but it's not a very common thing. And indeed, in some classic literature in cognitive science, going back to the 70s and 80s, it's shown that there's this sort of conflict in how people judge these arguments between what the logic of the argument is and what they believe about the conclusion. And in particular, this is a really shocking table in this paper where they show that if you compare the percent of the time that people say an argument is logically valid for valid and invalid arguments in the top and bottom rows, and believable and unbelievable conclusions in the left and right columns, what you can see is that if the conclusion is believable, people almost always endorse the argument as valid. But if the conclusion is unbelievable, people are more sensitive to the logical structure. It seems like they might actually be checking whether the argument is valid or not, but they're also biased away from saying it's valid. So that's a pretty interesting finding, and you all did better than these people in this paper, which is an interesting finding as well. So, right, so people are sensitive to the logical structure, at least in the case when the conclusion is unbelievable, but they seem to be biased by what the content is. But content effects are not only biases that harm our performance. And to illustrate this, let me show you another effect of content on reasoning, which is about reasoning about a rule. So this is a classic task from cognitive science, which you might have seen, called the Wason selection task. And the way this task works is that you give people a simple rule, like if there's an even number on one side of a card, then the card should have red on the other side. And you ask them, look at this set of cards and tell me which ones you need to check to try to falsify the rule, to see if the rule is being followed. So quick, which cards do you need to check? Red, green, even, odd? All right, I heard a mix of answers. So it turns out that when you ask most people, at least the kind of people who Wason evaluated in this paper, this question, they say you need to check the even numbered card, which is correct, and you need to check the card with red on it, which actually turns out to be wrong. So what you need to do is to check the even numbered card and the card that has orange, because if that card had an even number on the other side, then it would be breaking the rule. But it turns out that you can make this question much easier for people by putting the same logical structure into a slightly more familiar social setting. So for example, if you give them some cards and you say, these cards have ages on one side and beverages on the other side, and if they are drinking an alcoholic beverage, then they need to be over 21, 18 is it here? Then almost everyone will get it right, or at least a lot more people will get it right. So in this case, having familiar content in a rule doesn't just bias people's reasoning, it actually makes it easier for them to arrive at the correct conclusion. So across these two cases, human reasoning is not purely abstract logic, but instead it's something a little bit more subtle and content dependent. Now, in the language model case, there's been a lot of interest in language model reasoning about, what is that, 1 million papers or 140,000 papers since 2018. And these papers kind of span a spectrum, which ranges from people who think language models are more or less capable of reasoning. This is the original chain of thought paper. To people who say something like, well, language models are just some pile of tricks. And why would people be skeptical of reasoning capabilities in language models? Well, for example, this is from the GPT-3 paper, I believe, showing that as you get larger models, they get better at things like arithmetic. But it turns out that in many cases, you can show that there's weird patterns of biases in these responses. Like, language models are better at answering questions in arithmetic about numbers that occur frequently in the training distribution. Or, as I would phrase it, language models also seem to not be doing perfectly abstract reasoning, but rather to be doing something that depends on the content that they're reasoning about. So in many cases, in many ways, this seems to me like a case where the rationality wars are striking again. There are some people who are saying, oh, in these certain contexts, language models are doing something purely rational. They're doing rational reasoning. There's other people who are saying, oh, they're just a pile of tricks, heuristics, and biases, and so on. The question we want to ask in this work is, are these tricks similar to the ones that humans are using? And are the accurate reasoning similar to the things that humans are doing? That is, will the content effects on language model reasoning match the kind of content effects that have been observed in humans in the experiment I showed you before? So in this paper, we created a bunch of data sets for evaluating content effects in language models. I'm only going to show you a subset of these here. And just to note, because those prior experiments on like the Wason selection task are all over the internet, we created completely new versions of these tasks that have a similar structure to the previous work, but have entirely new content so that hopefully they won't have already been seen by the language models in training. So for the syllogisms task, one of the problems would look something like this. The model sees an argument, sees the two premises and then the conclusion, and then it has to produce an answer. Either this argument is invalid or this argument is valid. And this is the pattern of how often the model says the argument is valid by condition. So the green bars are the cases where the conclusion is sort of believable, seems consistent with reality. The purplish maroon bars are the ones where the conclusion sort of violates what people would expect. And you can ignore the gray bars, they're a sort of control nonsense condition. Then on the left, you have arguments that are actually valid. On the right, you have arguments that are invalid. And so first of all, like humans, this language model seems to show this bias by conclusion believability. That is, if the conclusion is believable, the greenish bars here, the model is almost always saying the argument is valid, regardless of its logical structure. Whereas if the conclusion is unbelievable, it's a little bit more sensitive to the logic. And it's actually quite shocking if you look numerically at the comparison between these answer proportions and those ones, just how closely the model is reproducing those human effects. Although that may depend on exactly which model you use and how the prompts are phrased and so on. But in this case, the model is quite consistently saying valid if the conclusion is believable and shows more sensitivity to logic if the conclusion is unbelievable, just like the humans do. For the Wason selection task, the prompt looks something like this. For a realistic rule, we give the model a tiny bit of context about what the rule is, like a parent needs to check that their children are following rules about playing video games and doing their homework. We give the model the 4 cards, and then we ask the model to complete a sentence like, you need to flip over the cards showing this and this. And if we compare performance on the realistic rules to the arbitrary rules, just like in prior work with humans, the model is much better at answering the realistic questions correctly. It's performing just below chance on the arbitrary ones. So like humans, the model is better able to reason about realistic rules than arbitrary ones. There's also some other interesting differences we talked about in the paper. In particular, there's a certain kind of rules where we shuffle realistic rules. We put together the pieces of 2 realistic rules in an unrealistic way. And interestingly, even in that case, the model is a little bit better at answering the questions. Of course, there's a lot of things you can try in the prompts that might affect how the model would produce its answers. And so it turns out that things like giving few-shot examples, reframing the problem, giving zero-shot prompts that say something like, consider these logical problems carefully, can all shift the way the model performs on these tasks, and in many cases can make the model less biased. So in other words, language models show at least some human-like content effects on reasoning on these syllogisms and rules tasks that have been observed in the literature. And I think this offers us an interesting opportunity to reflect on what reasoning is. So in the human cognitive literature and in the language model literature, there's been a variety of studies and papers and books debating whether these systems are actually capable of doing some sort of perfect abstract reasoning or just doing something more heuristic and biased. And what I'd like to propose is that these are sort of false dichotomies. It's not one or the other. Instead, we can think about normatively, that is, from first principles, why would a system be biased by content in its reasoning? Why wouldn't humans be perfectly logical reasoners? And I think the answer from my perspective is that reasoning isn't an end unto itself. It's there to help us achieve some goal in the world. Our goal is not to be logical reasoners. Our goal is to, survive and have a good life and whatever we're trying to do. And so if you think about the case of the Wei-San rules, it's actually the case that the content effects on reasoning help people to reason more accurately in precisely the cases that they're most likely to encounter, right? People are accurate at reasoning about social situations. That's the important thing to get right. You almost never encounter some weird arbitrary rule about cards with even numbers and colors. And so perhaps it's that content affects reasoning because it helps us to get the answer more right on average across the distribution of things that we encounter in the real world. And similarly for the language models, it helps them to do the same thing. It helps them to make more accurate predictions about which text will come next across the distribution of text they encounter on the internet. And I just want to highlight that this is certainly not a new idea. There's many cognitive accounts of these phenomena that provide similar accounts of why people use heuristics, why we're biased, and so on, again, often under the term of bounded rationality. But I think that the interesting addition from these experiments with language models is that you don't need to assume that the system is doing something very sophisticated to arrive at these answers. Like the system doesn't have to be doing some sort of planning where it's like, oh, I'm deciding whether I need to reason carefully about this, or I'm just deciding to allocate a more simpler strategy. You can actually get this from doing a very simple predictive learning mechanism across the right kind of data. Cool. So with that, I'd like to wrap up, and then if we have any time, we can take a couple more questions at the end. So to summarize, in this talk, I talked about language models and how to compare them to humans. Language models are these systems that are trained to do next word prediction using this vector attention operation. And why might that be cognitively interesting? Well, we think prediction is actually a pretty fundamental thing that the brain is doing, and they can do some pretty cool things, so it's interesting to think about them. But it turns out to be a little bit tricky to make fair comparisons between these systems because humans in the lab are sort of motivated. They have instructions and examples in a way that's easy for them to understand. Maybe they see diagrams and things like that. And it's hard to perfectly match these factors for the models. So as we said in our discussion earlier, we probably won't know how to make a perfectly fair comparison until it's been quite thoroughly explored in the literature for a long time, just as it has been in comparative psychology. But I think doing these comparisons is worthwhile because comparisons offer us opportunities to refine how we think about capabilities. So I showed you two examples of cases where humans are often presumed to have some competency for things like grammar and reasoning, but we actually make systematic errors in certain cases, and models can reproduce these kinds of phenomena and the kinds of cases where we get correct answers depending on how you frame the problem. And I think that what's exciting about this is that because language models are such different systems from humans, they're trained in a very different way, they don't have access to multimodal data, they don't have any sort of the same innate inductive biases that we do, it offers us an opportunity to ask, when they do the same thing, what is it that's the same between these systems? And I want to highlight some work from my colleague Stephanie Chan and from Ben Kristevsky at Stanford that have been doing this sort of thing, asking how, for example, statistical properties of the data distribution that models are trained on might explain some of the capabilities like in-context learning and reasoning that they exhibit, and connecting to how these things might come up in the experience of that humans and animals encounter too, and might explain some of our capabilities as well. Likewise, in the many cases where language models and humans produce different responses, it offers us an opportunity to ask what's different. To say, for example, oh, maybe you need some sort of instructions here. Maybe you would need a diagram that could explain things, and how would you give that to a model? Could you train a model with diagrams, and would it do better? And finally, it offers us an opportunity to consider some more fundamental questions like, how much of superficially complex cognitive abilities could you get just from doing very simple predictive learning across the right kind of data distribution? And how should we think about a capability? How can we define that if both humans and language models exhibit this sort of graded, sometimes biased, context-dependent performance? So with that, I'd like to thank my collaborators, in particular Ishita Dasgupta, who was co-first author on the reasoning work, Stephanie, Tony, Jay, Darsh, and Felix. And thank you all for listening. Happy to take any questions.